Hey all, good morning or good afternoon. I'm Itzhaki. I'm the CEO of Phoenix, and I'm going to talk about MPC, ZKP, FHE, and even a sprinkle of TEs, and in the context of which cryptography to bet on. Before starting to talk about the different technologies, I just want to give a brief overview about myself. I'm not a crypto native guy. I used to work at Intel for many years. Recently left Intel, and my job at Intel was the director of homomorphic encryption. And as part of the day job, I had to meet a lot of people out there. Some of them were developers, but some of them were just business-oriented. And every time I tried to explain the difference between ZKP, FHE, and MPC, I got a really vague look on their face. So I decided to try and explain this systematically, but actually try to keep it at a bit of a high level to make sure that people do understand. Now, we've all heard about these three-letter cryptography, some in the context of scaling, some in the context of privacy. I'll try to make a little bit of a order in that space. So before explaining what these cryptographics are all about, I want to take a minute and just explain why do we care about them. And I'm going to talk about it in the context of data confidentiality. So every time people hear about data confidentiality, they think about privacy, they think about protecting the users, and it's all true. But actually, we believe at Phoenix that there is a massive problem on the blockchain space today, which is that everything on-chain is public. Now, for some people, they may see it as kind of a feature of how blockchain works, but what I believe is that actually this is a limiting factor. And the reason is that this doesn't just expose users to their data being public. It also reduces our ability to develop new use cases that can actually grow the blockchain ecosystem. So I'm going to talk a little bit about a few examples, and then I'm going to talk about the different solutions. So I'll start with ones that are actually quite easy to understand, and I'll take an example of confidential transactions, where we're doing transactions on the blockchain. Everything is on-chain. You can actually see everything that's been ongoing there, which exposes users. And if we can get encryption on-chain, we can actually enhance the user security. If you take another example of on-chain gaming, like poker, that can't really operate in a trusted way if every bet that you make is public on-chain. And all the way to confidential voting, which I don't think I even need to understand why you need encryption on-chain. But this is just, I would say, the basic use cases. Things start to become way more interesting when we're going into the DeFi space, when we're trying to look at problems like MEV, when you want to look at solutions for MEV. And today, there are two paths to solve the MEV challenge. One is by encrypting the mempool, which clearly requires encryption. And the other path is also by using MEV auctions. And even then, when you do auctions, you need to have encryption to make the auction viable. And there are compliance pool and decentralized entities and account abstractions. All of these use cases would benefit from encryption and data confidentiality. So let's start about the cryptography that people heard the most, which is zero-knowledge proofs. I want to make sure that I use the term zero-knowledge proof versus just ZK, because people tend to forget that ZK is actually a proving mechanism. So what ZKP is, for folks who don't know, it's basically a cryptography method that enables one entity to prove to another entity that they know something without actually revealing what it is that they know. Kind of hard to understand how you can achieve that, but if you take that example that people typically tend to provide, which is an entity A that has two balls in their hand, one blue, one red, and another entity that wants to show that entity that they know they have balls with two different colors, but without revealing that they have a red ball on the right hand and a blue ball on the left hand, What they can actually do with ZKP is tell that entity to take the balls, put them behind their back, and flip them, or not, and show them again. And since they're able to see the color, they'll just be able to say, yeah, you've flipped them, or you've not. And if you do that a several amount of time, you can actually prove that you can see that this entity has different balls in their hands without actually revealing the colors of the balls. So that's like a very basic example. But when we think about ZKP in the blockchain space, typically it's being used in two domains. The first one is the one that everybody heard about, which is in rollup validation for scalability, being used by Starknet and zkSync and Scroll and Polygon. But when we start talking about using ZKP to address data confidentiality, it is actually quite limited in what it can offer. Because remember, ZKP is a proving mechanism. It does not enable you to do computation on data while it's encrypted, and as such, can provide confidentiality to a very small amount of use cases. If you want to do auctions, if you want to calculate on data that's coming from multiple entities, ZKP is not the solution. Another cryptography that's being mentioned is multi-party computation, or MPC. And MPC, in short, is basically a technology that enables a group of different owners to jointly compute a function of their private inputs. In layman terms, we can take a private key, take this private key, split it into shares, and then have each party do computation with that share. And only once everybody has completed their computation with that share, then the computation itself can actually be executed. MPC today in the blockchain domain is used mostly in digital asset custody wallets with Fireblocks and Zengo and Coinbase and others. And the reason is that it has a limited set of entities. Let's take the scenario of a custodian that you don't necessarily want to give a custodian full control over your private key. You actually want to have the ability to sign it and have another entity sign it together with you, and only then the transaction will be executed. That's where MPC is being used, and it's being used quite widely. The problem with MPC is that it requires significant communication and the bandwidth, especially when you're trying to work on the internet. So it is limited to use cases with a small set of participants. This picture here is taken from the storm last year in I-5, Portland, where I'm at, and I was stuck 4 hours in that storm in the car. So I'm not saying MPC takes 4 hours, but it is definitely slow and limited to a small set of users. And not to forget, there is also trusted execution environments, TEEs, which are a secure environment, typically within a CPU, that enables you to do computation in a secure fashion inside that trusted hardware. TEEs are great, they have good performance, but their security guarantee is lower than a cryptography guarantee, and they're prone to side channel attacks. So now I'll introduce the new kid on the block, and that is fully homomorphic encryption, or FHE in short. What FHE is, for those who don't know, is really a very novel cryptography. Actually, anybody who Googles FHE will see the term. It's the holy grail of encryption technologies. Because what FHE does, it enables you to do computation on data while it's encrypted. Take a minute and absorb this. You can do computation on data while the data is encrypted. So unlike any other encryption technology that requires you to decrypt the data before you can do computation on it, with FHE, you can actually do the computation on it. So how does it work? I've tried to explain to many people how FHE works, and I tried to use elaborate mechanisms, and I think everybody after 30 seconds just went to sleep. So I'm not going to try and explain it in a mathematical representation. I'll give an example. But I do want to make sure that people understand that the fully homomorphic encryption comes from the mathematical terms of homomorphism, which basically means that you're maintaining the same mathematical formation when you're moving from one structure to another. So I thought hard about the best way to explain what FHE is. I was on the plane, I saw Spider-Man enters the multiverse, and I thought, you know what, that may be a good example. So in essence, what we're doing when we're encrypting data with homomorphic encryption is we're basically transitioning it from one domain to another. The data is encrypted, but it actually maintains the same mathematical values that it has before the encryption. So given that we're maintaining the same mathematical formation, we can now actually do computation and after that decrypt the data. It's very similar to like when Spider-Man crosses the multiverse, so that's like the encryption part of it. When he's in the other realm, he's still maintaining the same information. You can do whatever you want with Spider-Man, and then when he comes back, he gains all the insights that he learned and at the other realm. So why do we care about FHE? Well, as I said, it's the holy grail of encryption. It's been discussed for many, many years, and there's been constant progression around FHE, actually. People tend to think that it's slow and compute intensive, and it is compute intensive, but there has been constant progression that actually makes FHE ready for prime time today. But the second part of it, it's actually that it's very easy to use. So with Phoenix, we're supporting Solidity, so we're EVM compatible. We're using a library from Zama. And what you can do as a developer is basically just use the same Solidity language that you use today, but you just have an additional function to encrypt or decrypt assets. You don't need to learn a new language. You don't need to understand what FHE is. It's basically just an ability to encrypt and decrypt very easily and very natively. Now, it's not just us that are excited. I think the market shows that. I've just put a picture here from the Masari report about top 10 trends to focus on in 2024, and FHE is one of them. So it definitely is transformational and going to make a whole lot of new use cases maturing. So in short, I'll talk briefly about Phoenix, and then I'll give an example of how all of it glues together. So Phoenix in itself is a layer 2 Ethereum compatible platform. We're built on top of the Arbitrum stack, and we can actually enable computation over data while it's encrypted, Solidity-based, very easy to use. So who should I bet on? I talked a lot about FHE, and maybe you think that FHE is the best solution, and I do think it's great, but actually, for solving the challenges, we need all three of them. We need the combination of ZKP, FHE, and MPC. And the reason for that is that we need zero-knowledge proofs to prove the correctness. So when a user encrypts data, we want to make sure that the data that is encrypted is proved and is verified, and that's where ZKP comes into place. We need FHE to do the computation on the data while it's encrypted, and we need MPC to protect the network key. So with that, I'll give just one example of private voting. We'll take an example of a private voting contract that initializes a new private and public key pairs. These private keys never exist in one place, thus usage of MPC. The users can encrypt their votes with 1 or 0, and that is through using the homomorphic encryption that I described. We use ZKP to prove that there is actually no double spending that's happening. And we have the validators that can actually tally all the votes without seeing these votes. And that is the usage of homomorphic encryption again. And at the time of reveal of the results, basically the validators decrypt the votes with no other data gets leaked. And again, this is using MPC. So with that, I'll end here. More than welcome to come and ask me questions after the presentation. Follow us on Twitter. And thanks for joining.